Okay, so let's talk about it. Okay, so first of all, let me copy it here because I'm not gonna have enough room anyway. So you know what, that's okay. So x minus 2 divided by x minus 2 and x minus 1. Domain is indeed whatever. I don't care to write it. I put everything in the table. So negative infinity to infinity, but not 1 and 2. Right? So far, so good? But if you don't simplify, you're making a mess. It will never finish.
I did. Why didn't you could find a derivative?
Of course. Oh, the simplified form, of course. Of course. So all you have to do is, first of all, determine when x is 0, so you get 0. Determine the end limits, same degree over same degree, so this is 1. So y equals 1 is a horizontal asymptote. X equals 1 is a vertical asymptote, and x equals 2 is a whole. You determine the limit left and right. So when you plug in 2, you have 2 over 1, which is 2. And here to the left of 1 with 0.9, you get negative infinity. To the right with 1.1, you get infinity. You're done. This should take like less than 3 minutes. And now I need to find the first derivative and the second derivative, and it's done. So f prime, top prime is 1 times x minus 1 minus the top times the denominator prime, which is 1, over x minus 1 squared. And you get negative 1 over x minus 1 squared, which is always negative. The function is always decreasing. And now you check, yeah, from 1 to 0 to negative infinity. Yes, yes. And now the second derivative should take another 3 seconds. So the first derivative goes negative x minus 1 to negative 2. So now when you differentiate, you get 2, x minus 1 to negative 3, or 2 over x minus 1 cubed. But for the study of the sign, you should see this. Just for the study of the sign. So the sign is given by x minus 1. Before 1 is negative, after 1 is positive. Done. That's all you need. So now you graph. You graph the asymptotes first. You have y equals 1. You have the vertical asymptote at 1. You have a whole 2 comma 2. Opening downward, decreasing from 1 to negative infinity, and crossing at the origin. And on the other side, from positive infinity going through the hole, oops, and approaching 1. And this is it. I mean, I was expecting 5 minutes. I was expecting 7 minutes, but not half an hour. Right? Is this clear?
And how'd you get y from 1?
By finding the limit. So when we find the limit of x over x minus 1 when x approaches infinity, it's infinity over infinity. You differentiate using L'Hopital's rule, and you get 1 over 1, which is 1. In the same way, you differentiate to get the limit at the other end, but there is no need. It's rational, so it will have the same horizontal asymptote at both ends. So this is the function x minus 2 over x squared minus 3x plus 2. So I'm hoping that you're going to start practicing this because this is our next test. So there are, as we mentioned, 3 major applications in this chapter. One is just this. The second one is optimization. And the third one, Newton's method. 3 applications. Being able to come up with everything about the function and graph it. Second application, optimization, which is an entire section. And the last one, which is a very small section on Newton's method. Okay. So, is this clear? Perfect. Okay. Good. So now let's look at section 4.5. although we know it quite well, it deals with L'Hopital's rule. I'm not going to repeat it. We know that it's applicable only inside a limit and only when the indeterminate cases are infinity over infinity or 0 over 0. But now, in this section, we are going to finally look at the other indeterminate cases. Total 7 indeterminate cases. The first two we played with quite a lot, so they are ratios. Infinity over infinity and 0 over 0. This is the only accepted indeterminate cases for L'Hopital's rule. Number 2, product. There is one product of 0 times infinity. Do not conclude anything. It's an indeterminate case. You can't say anything about it. It may be 1500. It may be 0. You don't know. Number 3, difference. We encountered this, not enough, so we're going to look at. So these are 4 already. 1, 2, 3, 4. And the last ones, and the most difficult to work with, are powers. There are 3. 0 raised to 0. It's an indeterminate case. 1 raised to infinity. Indeterminate. Do not conclude. You have no idea. It could be E. It could be E. It could be E squared. We don't know. And the last one is infinity raised to 0. You can conclude. You don't know. It can be anything. That's why they're called indeterminate. 7. 1, 2, 3, 4, 5, 6, 7. So in this section, we are going to go back to L'Hopital's rule. And we're going to look at several ones. Yes, I'm going to start with the easy ones. But then everything else, you can say, oh, wait a minute. How can you apply L'Hopital's rule here when L'Hopital's rule says clearly this or this? I have to manipulate the function and change all these into those. All these will be changed into those, so we can apply L'Hopital's rule. But some of them are more difficult than others. And the most difficult ones are these, the powers. The rest are easier. Well, the rest. These two are easier. These are more complicated. So let's choose problems. Next Monday, I'm going to have a copy of a previous test for you, so you can already start looking at it, okay, for test 3. Okay, on page 308, I will choose first to make sure that we choose the specific ones, and then I'll open discussion to whatever you want to choose. So page 308, I'm going to start with easy ones, just to refresh our memory. So number 18, limit as x approaches infinity from x plus x squared divided by 1 minus 2x squared. This is basically a warm-up. Why? Because we've done this in even more complicated situations than this. Okay, so first we have to. So this is another reinforcement why I specifically and kindly ask you always plug it in, because you need to know what is happening. Or maybe the answer is 5 and you don't have to do anything. So you must plug it in, okay? So we know what we're facing. Okay, so obviously it's infinity over infinity. We don't care about the sign. Yes, it's negative infinity in the denominator, but who cares? So since it's infinity over infinity, we're going to do what? L'Hopital's rule. Top prime is 1 plus 2x. Denominator is negative 4x. We check again by plugging it in, because it's still infinity over infinity. The sign doesn't matter. So then limit as x approaches infinity, the top is 2, the denominator is -4, and as we expected, same degree over same degree, the leading coefficient over the leading coefficient. We knew that from pre-calc. So it's -1/2. Which means y equals -1/2 horizontal asymptote. We've seen this before many times. Okay, so let's look at another warm-up, like, for example, 38. Please stop me if you have questions. Any questions on this problem, please? Don't let me move on. Any questions? Tom, everything okay?
Yeah.
Anything? Matt, anything? Okay, good. So 38, limit as x approaches 0 from e to the x minus e to -x minus 2x over x minus sine x. L'Hopital's rule is nice and friendly as long as the top doesn't have products and the bottom doesn't have products. Because you know the difficulty with the product is whenever we differentiate a product, we get a sum of 2 products. And we differentiate again 2 products and we get a sum of 4 products. And there is no end to it. So that's when things get complicated. But there are no sum. There's no sum at the top. There is no sum in the denominator. So I have to check. Because if the answer is 3, I'm done. I don't have to do anything. So can anyone tell us where the top is going? The top goes to? So this is 1. This is 1. That's 0. -2 times 0 is?
0.
So 0. And the denominator?
0.
0 indeed. Not a problem. We know that this is a friendly case. And there are no products. Top prime. Very good. But the next, exactly. Plus e to -x and minus 2. Awesome. The denominator. Excellent. We try again. Plug it in and please tell me what you get. The top. 0 over 0 indeed. Yes. So we apply L'Hopital's rule again. So what do we get at the top? Yes, e to the x. Yes, e to -x. Everything divided by? Very good, because cosine is negative. Cosine prime is negative sine x with minus in front. Excellent. Well done. Now what? I plug in again. What do I get? Yeah. Limit as x approaches 0. Over. Very good. Finally. So what's the top? What's the bottom? Very good. Awesome. It took us a while, right? We had to apply L'Hopital's rule several times, but we got it. Okay, now I'm looking for a difference, if I find one. Same page, 308. I don't like any of those differences, but I guess I'm going to have to pick one. I can make one up, because this is not what I had in mind, but let me look at the end of the chapter. Maybe there is something interesting there. Maybe a difference. I'm looking for a difference. A particular type of difference. If not, I can just pick the one that we have. Yep. So I'm going to pick 49 then. I don't want it to wait for me to check the results, so I have to check. I cannot just put it in. This is good enough, but this is not. I really wanted to look at a difference of two squares. The difference of two square roots. That's what I meant. But that's okay. I'll find one. Okay, so as we know, we have a limit law that allows us to say that the limit of a difference is the limit of the first minus the limit of the second. However, both limits have to exist. They have to be a number, but they're not. So this is 1 over 0, and this is 1 over 0. So I do have to change. You could say this is kind of infinity minus infinity, but it's really not, right? Because it's dne or minus dne. So it's not exactly what I was looking for. What should I do? We've done this before. We looked at this particular problem before. So obviously I have to find the least common denominator. And what is the least common denominator? Very good. So then this one needs to be multiplied by ln x and this one by x minus 1. So it gets a little bit complicated because of that product in the numerator and the product in the denominator. But we have to face it. We have no choice. Okay, perfect. Now I plug in, and let's see what we get. And in the meantime, I'm going to look back. There was a limit that I really liked, the difference of two square roots. So what do we do? I'm looking at the end of chapter 2 for a second. So what do we do here? We plug it in to see what it is. So what is it?
0.
It is 0 over 0. Perfect. Perfect. I found it. That's what I wanted. So we'll go back to this one in a minute. On page 167, this. That's what I had in mind. I thought that they would put something like that in that section, but there is nothing like that. Very good. So this is 0, this is 1, but this is 1, negative 1 plus 1, so indeed 0. This is 0 times 0, so it's 0. Still a friendly situation because it's 0 over 0. So now let's see. Let's start with the denominator. X minus 1 prime, 1. So times natural log x plus x minus 1 times. Excellent. I will distribute it first and then we'll see what happens. Good, let's go to the top. Again, I have to use the product rule on this. The first function prime, 1, natural log x, plus x times the second function prime. Very good. And then negative x prime. And then 1 prime, 0. Very good. Okay. So this is limit as x approaches 1. So I hope you agree that the numerator is natural log x, and x times 1 over x will be 1. But this 1 with the minus 1 will cancel out. Would you agree? So this is 1 minus 1, which is 0. So that's it that is left from the top. The denominator has natural log x. Now I will distribute. How much is x times 1 over x? X times 1 over x is 1. And we get negative 1 times 1 over x, which is negative 1 over x. This is a great achievement. Why? There are no more products. It happened that the products went away. And that is good. Okay, now we check again. The top, 0. The bottom, 0. Okay, we're close. So limit as x approaches 1. The top prime. Excellent. The denominator prime. 1 over x minus. It's very important to remember that 1 over x prime is 1 over x squared. With minus in front is positive. There is something common in the denominator that will go away with what I see in the numerator. So what will you factor out from the denominator that will go away with the numerator? Indeed. Indeed. That's my hope. But let's see what is left. You have to give me two terms. The first term will be 1 plus. Indeed. Awesome. So now we got rid of 1 over x. The top goes to 1. The denominator goes to 2. And that's it. So when we go back to this list, basically all we have done so far are still these two. We still have not seen any of this yet. Here's our next example that I just picked. That's going to be the next one. Here it is. Limit as x approaches infinity from the square root of x squared plus 4x plus 1 minus x. We've done this before. We've seen this before. On any problem, we don't have to use L'Hopital's rule. But this is the case, infinity minus infinity. Because the first portion approaches infinity, the second portion approaches negative infinity. And yes, so it's infinity over infinity. I can't do anything just yet. I have to, as the starting point, I still have to what? What did we do in the past? This is the same thing I have to do now, or at least as the first step. I have no choice. What was it? We rationalize indeed. There is no other way. So we multiply by the square root of x squared plus 4x plus 1 plus x over the square root of x squared plus 4x plus 1 plus x. So then limit as x approaches infinity. And the numerator is x squared plus 4x plus 1 minus, very good, x squared. Very good. Now, since last time when we worked on this problem, we did not know L'Hopital's rule because it was in chapter 2. Let's give it a shot. If it gets too complicated, then we can still factor out. So let's try. When I plug it in, the numerator is infinity. Obviously, the denominator is infinity. So as you saw, we initially started with infinity minus infinity, which is the only difference in the determinate case that we had no idea. And now it turned into, yes, it turned into a ratio, one of these two, and we're able to apply L'Hopital's rule. Very good. Okay, so let's see if it works and how. So limit as x approaches infinity. We differentiate the top and it's nice. We get 4. Perfect. Let's see what happens with the rest. We differentiate this. 1 over 2 the square root of x squared plus 4x plus 1 times 2x plus 4. And this is plus 1. The reason I'm saying that maybe this works with L'Hopital's rule is because it may get super complicated because it's going to be a ratio. Who knows? I have to simplify it first and see what happens. So, of course, I will factor out 2 and simplify with this 2. Limit as x approaches infinity. 4 over, and this will be x plus 2 over the square root of x squared plus 4x plus 1, and then plus 1. Okay. For now, I can already say I would have preferred to factor. I would have simplified by now. But we want to see what works and how it works with L'Hopital's rule if. So limit as x approaches infinity. I still have 4 over x plus 2 plus the square root of x squared plus 4x plus 1. Everything divided by the square root that I'm going to put at the top. It turns into a mess. That's what I said. Why is it a mess? First of all, because when I differentiate the top, I'm going to get again 4, 1 over 2, the square root of that, times 2x plus 4. When I differentiate the denominator, I'm going to get again 1 plus 1 over the square root, 2 the square root of x squared plus 4x plus 1 times 2x plus 4. And I don't see an end to it. Well, let's give it a shot. It's still infinity over infinity, just one more step. And then we can give up and go back to the previous method. Maybe that's why they didn't put 1 in this section, because it has no end. Okay, limit. Okay, so if I differentiate because it's infinity over infinity, then it's 4 times 1 over 2 the square root of x squared plus 4x plus 1 times 2x plus 2. I'm sorry, 2x plus 4, of course. Everything divided by 1 plus 1 over 2 the square root of x squared plus 4x plus 1 times 2x plus 4. And I could get rid of the denominator if I simplify. But then I still have this, the 2 the square root plus x plus 2, or just the square root of x squared plus 4x plus 1 times x plus 2. And I can't get rid of this. That's the problem. Now, if I keep it as is and I try to simplify, to differentiate, then when I differentiate this is a ratio, and it gets even more complicated. So let me just show one more step since we're here, because now I'm curious. So the 2 from here with the 2, so these 2 go away, so there is still a 4, which I can put in front of the limit. I don't care for it. So the numerator is x plus 2. The denominator is the square root of x squared plus 4x plus 1. Now here it's again the square root of x squared plus 4x plus 1 and plus x plus 2 over the square root of x squared plus 4x plus 1. And I go around in circles. Because even if I flip and I get rid of the square root, the numerator would be still 4 when I differentiate, but I get again to differentiate the square root. So this is a perfect example. I wanted to go through it. I didn't know what to expect, but I wanted to go through it to show you that L'Hopital's rule sometimes is way too complicated. And I don't even see the end of it because of the square root. So if you remember how we solved this problem, was to factor out x squared, factor out x in the numerator, and we got whatever. I don't remember, 4 over something, potentially 2. So now let's finish it up because we started it. So I'm just going to continue from here without L'Hopital's rule. So the numerator, we factor out x, so we have 4 plus 1 over x. And the denominator, we have x outside because it's the absolute value, but it's approaching infinity. So we have 1 plus 4 over x plus 1 over x squared and plus x. So finally, this is should be in your notes in chapter 2. So we have 4 plus 1 over x, and the x goes away, so the square root of 1 plus 4 over x plus 1 over x squared plus 1. So this goes to 0, this goes to 0, this goes to 0, and that's indeed 4 over 2, which is 2. So y equals 2. horizontal asymptote at infinity only. We have not checked negative infinity. So that was a much more straightforward step to factor out the degree at the top, the degree in the denominator under the square root, and then factor out x and simplify. But this, even if I try to simplify, I won't be able to get anywhere. So don't erase anything. This is a very good example, but we can finish it up using that method. Good. So far we saw this. We saw for this particular example that L'Hopital's rule was really ugly. So now let's look at these three situations. Let's try this one first. And the other three, and oops, where's my 6? Where's my 5? It's 5 and 6. Okay. And then I'll let you choose. So back to page 308. Okay. Yes. Let's look at 46. Same page. Limit x times tangent 1 over x when x approaches infinity. Okay. When x approaches infinity, where does this go? 0, very good. Where does this go? Very good. Where does this go when x approaches infinity? Very good. 0 times infinity. So this is the product of indeterminate case. Do not be afraid of this one, because this one should not be a big deal. I can say a guarantee for everything, but should not be a big deal. With a very simple algebraic manipulation, we are going to get what we want. So we understand that when I divide these two fractions, tangent over 1 and 1 over x, I have to flip 1 over x, and I get that. So I only rearrange the function. So when you divide this, you flip x and you get this. But now I get exactly what I want. So through a simple algebraic manipulation, I got what I wanted. What do I want? I want 0 over 0, right? That's okay. So this tangent is still at the top. It's still approaching 0 when x approaches infinity. And now the denominator 1 over infinity is 0. And so this particular situation is nice for this particular case. Maybe other cases may be more difficult, but for this situation, the product was easily, for this problem, easily turned into a ratio. So now we will differentiate the top using L'Hopital's rule, and we get, excellent, secant squared 1 over x times, yes, negative 1 over x squared. And when we differentiate the denominator, we get, excellent, couldn't be better. So now when x approaches infinity, this approaches 0. And how much is secant 0, or how much is cosine 0? Because secant is 1 over cosine. Once I know cosine, I know secant. 1. So the answer is 1. So y equals 1 is a horizontal asymptote for this function at infinity. Any questions? Any questions? Okay, let's look at one more for the product. Let's say 42. Limit, and then we look at the ugly ones. The square root of x e to negative x over 2. Okay. When x approaches infinity, where does negative x over 2 go? Perfect. Indeed. This indeed goes to negative infinity. Where does this go? Very good. Where does this go when x approaches infinity? Right. So we're back to the same situation. But now the question is, what do I do? I have to change it into a ratio somehow. Which portion of this product would you try to manipulate? Say it again. That would be a very difficult situation, because then I'll bring it down and I'll have x to negative 1/2. So if not the square root of x, then yes, because that one already has a negative exponent. It doesn't really belong at the top. So limit as x approaches infinity, the square root of x e to negative x over 2 can be rewritten as the square root of x over e to x over 2. Right? It already has a negative exponent. It shouldn't even be at the top. It's intentional, right? So now where does the top go? Where does the denominator go? So this is infinity. Now e to infinity is, yep. Once we brought it down, it has a different story. So now this is x approaches infinity. 1 over 2 the square root of x over e to x over 2 times 1/2. So I keep 1 over 2 the square root of x, and I flip 2 over e to x over 2. Because this is e to x over 2 becomes 2 over e to x over 2. So where does this, after I simplify? The numerator goes to 1. The denominator goes to, I shouldn't write it here. I should write it here. The denominator goes to infinity, and 1 over infinity is a very nice number, which is 0. So y equals 0, horizontal asymptote at infinity. Any questions? Okay, we delayed enough. So now we want to look at the ones that I consider most challenging. Now we're going to look at the powers. Okay? This was 9, right? 10. That's the last step in this section. Okay, 62 on 308. Limit as x approaches, I see infinity, e to the x plus x raised to 1 over x. Not a nice situation. Not friendly at all. Okay, where does this go? Where does this go? And where does the sum go when x approaches infinity? Of course. Where does this go when x approaches infinity? Right. This is a situation of one of the 3 powers. Infinity to 0, 1 to infinity, 0 to 0. So it's one of them. Okay, well, in all these powers, we would have to use a function that brings the power down. What is that function that brings the power down? And there is only one. Yeah, that's what I say. It's not a friendly situation. We will have to denote the function by y, we will have to apply natural log to both sides. And now we're going to do something that I promised a long time ago. There is a theorem, and we've used it several times. But that theorem without that theorem, we cannot do this. What was that theorem? Swapping of the operators. We have to find the limit of natural log. And you can say, but that's not what we're asked to do. I know. So once we apply log to both sides, we have this, and we have to apply limit to both sides now. So the limit of natural log y when x approaches infinity is limit as x approaches infinity, and I'm going to write it as a fraction, of natural log e to the x plus x over x. And yes, I know this is not what we are asked to do, but we have no choice. Like we couldn't differentiate x to the square root of x. We don't have a rule for a function raised to a function. We had to use natural log. Okay, so now again I have to plug it in. And I'm hoping for a ratio, of course. I'm hoping that I got away from this. And I did. So the top goes to, the bottom goes to, we're in business. So then this is limit as x approaches infinity, the top. Careful. Excellent. Times. Yes. Excellent. The denominator. Exactly. Great. We're not done yet. So I copy. Now this is the limit as x approaches infinity from e to the x plus 1 over e to the x plus x. What is it? Good. That's good. That's not bad. That's very good. X approaches infinity, the top. The bottom. It's still infinity over infinity. So now limit as x approaches infinity, e to the x over e to the x, and I know the answer. 1. We haven't finished. Now we go back to our starting point. This is our starting point. And this is our end point. I'm going to copy the start and the end. Limit of natural log y as x approaches infinity is 1. Because this function is continuous, I am allowed to swap the operators. What would you write? These are the two operators that need to be swapped under conditions of continuity. Natural log of limit of x when x approaches infinity of y, and this is exactly what I want to determine. After swapping of the operator, I got exactly what I want, because this is y. And now we have to think, what can this be? Natural log of something equals 1. And it's only one number. There is no natural log of 0. Exactly. Exactly. This must be e. There's no way there is anything else but e. So I finally have the answer. You didn't expect that, did you? That infinity raised to 0 to turn out to be e. You can't say that you were expecting that. So then limit as x approaches infinity from e to the x plus x, everything to 1 over x, is e. And now you understand why this is the most difficult situation, because we are starting with the product And there is no way, we have to apply natural log, then we apply the limit to natural log, then we swap the operators, and then we have to think, what can it be? A lot of steps. So let's look at the next one.